We're going to go over the velocity selector. I did that with you when we did the mass spectrometer. A velocity selector uses what we call a cross field, which means it has two fields. It has an electric field and then it has a magnetic field. So there are two fields. These two fields, right, will make sure that your ion that's coming out go horizontal. So generally the case, I'm going to apply that there in a minute. Generally in the case, you could have, let's say this is positive. If I want my electric force to go up, what does that mean? Well, that means I need to have a negative plate here and I have to have a positive plate here. Yes or no? Makes sense, doesn't it? The velocity selector will specifically choose ions of a certain velocity because you cannot measure the velocity of the ion. Are you going to be able to time this? Say, all right, here's distance, here's time. You can't. You have to work it out using this principle. We've got that. So in blue now, I'm going to do the magnetic field. If I now have a magnetic force going down, what's the force on the charge? Anyone? What's the force on the charge in the magnetic field? BQV. So my FB is equal to BQV. And what do we use for that? Fleming's left-hand rule. That's current, conventional current. So where's the charge traveling? This way. The charge is traveling here with a velocity v. It's going this way. Yeah? Where's the force? Going down. So where's the field? Coming out of the plane of the board, right? How do we draw that? Dot. Yeah? Remember that? Dot and cross arrow, the tip of the arrow. That's coming out, the back of the arrow. Does that make sense? So in a velocity selector, you could adjust the values for your electric field by V over D. You could adjust the value of your magnetic field by using your Helmholtz coil until you get your ions to come what? Horizontally. Yes or no? If the ion is coming out horizontally, in my example, what does it mean? Well, it means that my FE is equal to what? My FB. This is not my example, by the way. The questions one is different. I'm going to apply in a minute. What does that mean now? FB is BQV. FE is charged by E, which is also charged by V by D. Well, what cancels out? Q cancels out. I could use this one actually. E, velocity, is the ratio of the electric field strength to the magnetic field strength. Do you know the electric field strength? Yes, you're applying that field. You're applying the voltage. You decide that distance. So you know the value for E. Magnetic field, you're choosing that. You're choosing that magnetic field. You know the value. Could you work out the velocity for the horizontal one? Yes. This is what this question was about. Right? So now I've gone through the theory. Let's do this question. A positively charged. So if this ion is positive and this is positive, where's the electric force? This way. If it's going horizontally, where would be the magnetic force? Let's do it. I know it's going to be up, but I'm going to prove it. Field. Sorry, current. Conventional current, flow positive. Where's the field? Into the board. How do I know that? That little cross here. So where's the magnetic force? Up. The magnetic force is there. Right? So the question is then asking me for what? Calculate the magnetic flux density. It's asking me to work out B. So because it goes horizontally, the forces are balanced. And like we did earlier, FB is equal to FE. FB is BQV is equal to, how's it giving me? Yes, I'm going to use QE, but instead I'm going to do V by D. Yeah? Right. What crosses out? Q crosses out. B is equal to potential difference divided by the separation of the plates divided by the velocity. Was V given? Yes. So that was 5,000. Was D given? 2.4 separation. So that becomes 2.4 centimeters times 10 to the power minus 2. Was V given? Calculator person, try and put that in your calculator, please. 6 times 10 to the power of 6. What does that give you? Can you work it out? We said the answer was what? Is it? Yay, that's it.